All right, this is 3.3, logarithmic functions and their graphs. So we have three things we want to accomplish. We want to accomplish to be able to convert equations between logarithmic form and exponential form. We want to be able to evaluate common and natural logs, and then we want to be able to graph the common and natural log functions. Okay, so right here you see the graph of the log function. Now if you notice, okay, that the exponential functions that we've been graphing, the exponential function and the logarithmic function are inverses of each other. Okay, so this is what this red graph, this g of x, that is the basic graph for the log. Okay, now you can see here's the exponential function, just sort of another picture. And then up here you can see the natural log function, which is y equals ln x, and y equals log x. Now you might say, well, what's the big difference? Well, the big difference is the natural log is base e. Okay? So that's a fixed base every time. The log function, the base varies. So in other words, it's not going to be the same base every time. It could be base 2, base 5, base 10. Okay? That's why these graphs look a little bit different. And again, the exponential function we've already talked about. Come on, there we go. All right, so logs. Okay, we're going to change between logarithmic and exponential form. All right, so really what happens is that the subscript is the base, what the log equals is the exponent, and then what you're taking the log of is what the exponential equation equals. Okay, so this statement says that a logarithm is an exponent. Because logs are exponents, we can evaluate simple log expressions using our understanding of exponents. For example, okay, now when we do something like log base 2 of 8, that's how you read it, log base 2 of 8. What we're trying to say is 2 to what power is 8? Okay, now I'm assuming that we all know that that's 3. Okay, for part B, we have log base 3 of radical 3. Okay? Now, what happens here is that the square root of 3, that's the same as saying log base 3 of 3. Well, let me write this a little smaller. Okay? So I have log, actually, we're trying not to screw this up, guys. This is the same as log base 3 of 3 to the 1/2 power, right? Square root is a 1/2 power. Now, we have a rule, okay? All right, we have 3. I'm going to even just, this is a preview of the properties for exponents. That's not till the next section, but we're going to give you a little preview right now. What you would do is when you have a log of something to a power, that power goes out front. So it's 1/2 log base 3 of 3. Now, log base 3 of 3. So 3 to what power is 3? Well, that's just 1. So it's 1/2 times 1. So it's 1/2. Now, part C, okay, we have 5 to what power equals 1 over 25. Okay, now, how can I rewrite that? Well, 5 to the x equals 1 over 5 squared. Okay, so I changed 25 to 5 squared. But 1 over 5 squared is the same as 5 to the negative 2. Okay, so x is negative 2. Log base 4 of 1. So 4 to what power is 1? Well, the only answer that can possibly be is, whoops, learn how to write. I can't write. Okay. 0. 4 to the 0 power is 1. And then we kind of talked about it in part B. 7 to what power is 7? Well, 7 to the first. Okay, so that's how you evaluate the logs. All right, basic properties. This is important information. So the log base b of 1 equals 0 because b to the 0 equals 1. You can kind of see what happens here. The only one I really want to point out is the last one, because And actually, this one right here, the second to last one, we used for part B. I kind of gave you the long way, but that's the rule. Okay, these two rules you want to really lock in on. All right, so basically we just did the same thing. Look at that. So we already know that that's 3. We already know that that's 1/2. Now, part C is an example of that. You have b. Now, the log base b of x is in the exponent. But really what happens is that the answer is just whatever that is. So here the answer is just 11. Okay. All right, this is just a table to show you that if you have an exponential function and you have the log function, those are inverses of each other. Notice how the x and f of x columns switch. That is an indication of inverse. Okay, so this is just, information for you to have that illustrates the relationship between the exponential function and its inverse. Common logs are base 10. Okay, you never see a log with a subscript 10. It's just log, like here you see log 1. That's log base 10 of 1. Anytime you don't see a subscript, that means you have a base 10. So the log of 1 is 0 because 10 to the 0 equals 1. Log 10 equals 1 because 10 to the first is 10. And then 10 to the y equals y because, log of 10 to the y is y. And again, notice those last two rules. Okay. So the log of 100, the log of 100 is 2 because 10 squared equals 100. Okay. Now the fifth root of 10 we can write as 10 to the 1/5 power. So that means our answer is 1/5. Here we can write 1 over 1,000 as 10 to the -3. So our answer would be -3. Again, I'm just using these properties right here. 10 to the log 6 is just 6. It's whatever you're taking the log of. Okay? These are pretty simple, guys, as long as you follow those basic rules. Okay, this is even easier. Evaluating common logs with a calculator. So you've probably been wondering the whole time, hey, when am I going to get to use my calculator? Because that's what you all do. Well, you can really only use your calculator for the common log. Okay, so literally, the common log can be evaluated by using the log key on your calculator. So you literally press log 34.5, enter, and it will tell you what it is. So this is just a calculator exercise. I'm not even going to go through that. Okay, now, to solve simple logarithmic equations, so we have to solve each equation by changing it to exponential form. Well, what do we have? We have log x equals 3. What's the base? There is no subscript, so the base is 10. What the equation equals is the exponent. And then the only thing left is the x. So 10 to the third is 1,000. So x is 1,000. Now, notice what happens here. Okay? We have a base 2 because 2 is the subscript. So 2 is the base. Again, whatever the equation equals is 5. Or whatever the equation equals is the exponent, excuse me. So it's 5 equals x. Well, 2 to the 5th, 32. Okay? It's really that simple. E. Okay? So, natural logs are logarithms with base e. So anytime you see an ln, we are dealing in base e. Okay? Now, the basic properties for natural logs are the same as they are for common logs and for other logs. ln 1 equals 0 because e to the 0 equals 1. ln e equals 1. This is a big one. Okay, these two right here are big ones. Now, they're all big, but the first two are big ones because we're going to use those a lot. So, we have ln of square root of e. So to solve that, we do ln e to the 1/2 power because square root of e is e to the 1/2. So our answer is 1/2. Here our answer is 5. Here our answer is 4. Okay, we're just taking the exponents. Okay, that's all we're doing. It's that easy. It's literally that easy. Okay, you can put these in your calculator. I believe the ln button, let me get out my calculator here while my chair's creaking. The ln button, it's actually the ln button is prominent on your calculator. It's right below the log button. So you would literally press ln and then 23.5 and hit enter, and that would be your answer. Okay, so again, calculator exercise, guys, you can handle it. All right, last part, okay, and this is we're going to spend a few minutes on because we're talking about the graphs. All right, describe how to transform the graph. Well, for part A, while I put my calculator away, sorry, background noise, let you know how real this is. This is very real, okay? So, and my chair needs WD-40. So, anywho, part A. Now, these transformations are just like all the other transformations we've done, guys, okay? We are shifting, so we're going to shift ln x to the left 2. So it's a horizontal translation, okay, to the left 2. Now, when it says to graph it, well, it just says describe, so we don't even have to graph it. Okay? Now, part B, we saw this 3 minus x before, all right? So really what this is, okay, if you want to think about it this way, it's really -1 times x minus 3. Now, you might say, well, how did you get that? Well, what I did here was I switched the two terms around, okay? So I just switched the 3 and the minus x, and then I just factored out a -1, excuse me. Okay? So now, here's what that means. It doesn't equal anything, dummy. Okay. So we are going to reflect, okay, we're going to reflect across the y-axis, okay, and then shift, sorry for my writing, right 3. Wow, that's terrible handwriting. Maybe the worst of all time. Okay, so again, these are our normal transformations. Nothing big is happening. C, 3 is in front. So we vertically, it's a vertical stretch by a factor of 3. Okay. Now the last one, part D, okay. Now it's 1 plus log x. Now if you really want to get crazy with it, you could just reverse this and just write log x plus 1. Now, what do you notice? There are no parentheses, okay. So the log x, the log x stands alone. So that means with the plus 1 after it, what that means is we have a shift up 1. So we take the graph and we shift it up 1. Okay? So when you're describing the transformations, guys, it's like any other problems we've ever done. All right? And that wraps it up. This is not, I mean, there's a lot of examples, but it's not a hard section. Okay? You guys should be able to do very well with this.